Hi all, do you hear me? Do you see me? Okay, thanks. Right. So last time we started looking at RDF, Resource Description Framework. For fun, I had a look at Wikipedia, what it says about RDF, and basically it gives a pretty nice account of what RDF is about. So I really recommend this little page. It gives some examples. It says why RDF is needed, where it is used, and so on and so forth. It also gives a quick survey of the syntaxes, the syntactic representations, or they how they call it, data serialization formats. By the way, if you look at this page, then it itself contains some information in RDF. Yeah, in the if you look at this box on the right-hand side. Yeah, so it describes RDF1 in terms of its status, year started, editors, and so on. Yeah, so these are examples of triples. Yeah, it also gives a nice overview of the language, that the RDF data model is similar to classical conceptual modeling approaches. Well, I don't want to go through the whole page. I wanted to use one example. Where is it? Oh yeah, so it says that there are a few languages, a few serialization formats. At the bottom, you see RDF XML. This is what we saw last time. And today we are going to look at the first one, at the Turtle language, Turtle, human-friendly format. But first we have to finish the definitions of RDF and RDF schema. And where is the example? Oh yeah, so the example is here. It is, they write it's taken from the official W3C document. And what do we have here? If you read the first sentence, it's example one, description of a person named Eric Miller. So example is like this. We have a statement, or statements rather. There is a person identified by some URI, HTTP, whose name is Eric Miller, whose email address is the address there, and whose title is doctor. Right, so what's the idea of RDF? The idea is to represent information like this, or any other kind of information, in terms of triples, which in grammar, Russian, English, whatever grammar, corresponds to triples. Subject, predicate, and object. So what I wanted, why I needed this simple example, because here the structure of triples is pretty clear, right? So apparently the resource, let's read again. There is a person identified by boom, and this boom is the subject. Yeah, this is a URI. We start with this URI. It refers to the subject. All right, and then whose name is, right. Then we start with this URI. Then the property will be whose name is, and then the object will be Eric Miller. Yeah, and then again, URI whose email address is. That's another property. And the value of the property, that is the object, is the email address. And so on. So if I click here, hopefully, yeah, I get a picture. And this is a the RDF graph. So what do we have here? We have the node where everything, all arrows start, is the subject, and then there are 1, 2, 3, 4 triples. Yeah, the first one is the leading to doctor, is the personal title, and so on. Now look at the top arrow. It's a special arrow which gives, which says that this person is, sorry, that this individual is of type person. Yeah, so this person is a very special object. Yeah, in fact, it must be a class. Yeah, and you can further say, for example, that every person is a human being or something like that. And then this will mean that person is a subclass of human being. And this is exactly where we stopped last time. This is about the RDF schema. So I'm going to the slides now. Oh, sorry. I wanted to say one more thing, how to get rid of this. Okay, so we are back, and what I wanted to say is that this picture is a graph representation. That is why they say that it's an RDF graph. Yeah, it's a directed or oriented graph. Nodes are URIs or literals, or actually blank nodes as well. We'll come back to them. But in computers, this information, these graphs are represented by a certain syntax, or there is a variety of representations like this. And what we saw last time is this representation, yeah, in the middle. This unreadable XML, RDF XML syntax. Yeah, and I tried to explain how to read this syntax. Today, after we finish with this RDF schema, we'll consider the so-called turtle syntax, yeah, which is in the box on top. Yeah, it's way easier, and people, or we can actually read it. So this is the plan for today, and maybe if we have time, we'll consider a few examples. Next time, we are going to look at the query language for data represented as RDF triples. Okay, that's the introduction. So where are we? Where is the schema? Right, so we are considering RDF schema, yeah, where we deal not with the concrete individuals. John loves Mary. Yeah, here we represent John as a URI, loves also as a URI, all these resources, and Mary as a URI. And they refer, John and Mary refer to concrete individuals identified by their URIs somewhere on the web or elsewhere in some data set. And loves is also a URI described, I don't know, or by some community efforts in some vocabulary. Now, the schema, the RDF schema here, no, I need, let it be green. The schema. It deals with a higher level of things, namely with the classes, properties, subclasses, types, this kind of things. Yeah, because this involves reasoning. This involves some elementary deductions which the computer should be able to do on its own. Right, so quickly let me repeat where we stopped last time. So there are a few built-in, a few standard classes. Yeah, they are listed here. So in RDF, we have the class of all resources, and we assume that everything is a resource. We have a class of all classes. We have the class of all literals. We have the class of all properties. We have the class of all statements. For a philosopher, that would be probably interesting. We'll come to this a bit later. Yeah, and in this example, in the XML syntax, it's written that this thingy is of type class. And this thingy is of type property, that is binary relation. Okay. So those, sorry, just a second. Yeah, so those were standard classes. And we have also standard properties. Yeah, so for properties, we have RDF type, which relates a resource to its class. Yeah, Jane is of type girl. Yeah, and we draw it like this. So this is a URI, say, for Jane. And here we write RDF type. And here we write, I don't know, girl. So note that it's written RDF type, not RDFS type, because RDF, this type property belongs to the RDF, the core RDF. Now, what else do we have? We have subclass, yeah, which corresponds to set theoretic subset, and we have subproperty, also set theoretic subset, but over binary relations. Okay, we have seen this. Yeah, and this is new. So apart from basic classes and properties, we also have some restrictions on properties. Yeah, so we have things that are called RDFS domain and RDFS range. So remember that if we have a binary relation, say relation R, yeah, then what can be on the left is the domain of the relation, and what can be on the right is the range. So this is range, and this is domain. Yes, and RDFS allows us to describe the domain and range of relations. Now, for example, loves probably means that the domain is, I don't know, person, and the range is also person. Yeah, so RDFS domain specifies the domain of a property. RDFS range specifies the range of a property. And it's quite useful. For example, in the XML syntax, what do I have here? I have a property is taught by. Is taught by, right? So this X is taught by, I don't know, y. So what can be x? X can be something that can be taught, right? What it's a course, module, something like this. Yeah, so we say that is taught by has domain. So where can this thing be? It's a module. Yeah, and this is what I write. RDFS domain resource module. Yeah, what could be the range? The range could be what? It's well, here I would say it's an academic staff member. In Moscow, you would say преподаватель or препод or whatever. Yeah, so something like this. So here I write academic staff. By the way, I think it's very important to observe here that here I have module, yeah, or course or lecture, and both module and ACK staff are classes. Yeah, so we may have different modules taught by different academic staff members, yeah, and they are organized in these classes. Okay, so the domain of is taught by is a subset of the class module, and the range is a subset of academic staff. Okay, I'll give you only one bad example, saying that you should be careful when you deal with domains and ranges. Careful in the following sense. Okay, let's have a look at the example. So the example says that we have a property, author of. Yeah, like an author of a book. Yeah, and in one context, somebody writes, okay, suppose that the range of author of is textbook. Yeah, so author of, and here it can only be textbook. Okay, and somebody else, or the same person elsewhere, adds, because of whatever different interests or something, that, oh, the range actually is crime fiction, right? So then what the reasoner behind this document is going to deduce. Yeah? So this says that it's crime fiction. Yeah, the reasoner will deduce that whenever you have an arrow like this, then the end must be in the intersection. So it's both textbook and crime fiction. Yeah, so if you specify that a property has two ranges, then the system will take the intersection. 3, the intersection of all 3. There is another example, but it's not that important. All right, then in the next 5 minutes, I'll just I'll show you some basic rules that are behind the RDF reasoner. This very what do you mean, Lisa? The lectures are available and on the website. I have no clue. As far as I understand, the lectures are recorded. Maybe this one is being recorded at the moment. You should ask the. Actually, somebody checked last time and found a video somewhere. So my answer is yes, it must be the case, but ask. I don't know. Okay, thank you. Right. So what I wanted to say now is the following, that when we consider the this piece of RDF from the last lecture. Yeah, so we have, say, a semantic web module is stored by MZ, yeah, this triple. And then we also had that SW is of type module, this one. And MZ is of type professor. Now, what is RDF? Where is RDF and where is RDF schema? So roughly this dashed line separates this one separates the RDF and the schema. Type is still belongs to the RDF layer, and above it there is the RDFS layer. So let's look at the RDFS, because this is where reasoning is needed. So we have professor and we have module. And for module, we have no, wait a second. We have nothing. Let's start with the professor. Professor, and here it's written RDFS subclass of academic staff. Yeah, which means every professor must be also an academic staff member, which means that the reasoner should be able to derive that here we also have RDF type, right? Because an element of a class, which is a subclass of another class, of course, is an element of that second class. Okay, then what else? We have is stored by. Is stored by, as we saw earlier, has range academic staff and has domain module. Yeah, and I also showed you that there can be a more general property, say involves. Yeah, it doesn't mean that it, teaches. Yeah, it's somehow involves. I don't know. It can be, say, some technical support. So it can be a more general property. Okay, so that's the beginning. And as I showed you with this arrow here, some information is hidden. Right, and so what are the rules that allow the reasoner to extract all the hidden information? And so my question is, what implicit knowledge is missing in the picture? Yeah, and actually, you see that here we have, I don't know, 1, 2, okay, whatever, 10 arrows, 7 ellipses. Yeah, I wonder how many arrows and ellipses we'll have in the very end. Yeah, when we include all the hidden information. Okay, let's start with the following. You remember I started by saying that RDFS contains some predefined classes. Yeah, say RDF class, RDF property, RDFS resource. Everything is a resource. So in some sense, everything is should be of type resource. So there should be arrows from everything to resource. Yeah, say MZ is a class. So, oops, no, MZ isn't a class here. Professor is a class. Yeah, how the reasoner produces such errors, makes such deductions. Using a certain rules, using a certain set of rules, I'd say. And RDFS has about 30, I forgot, 35 rules. I'll just give you some hints of how these rules were introduced. Okay, so suppose we have a triple like this. X, RDF type, C. Like on the previous page, what did I have? I had this bit. MZ, RDF type, professor. Then from this, I deduce that professor must be a class. If MZ is of type professor, professor must be a class. Okay, and these are the rules. So if I have this triple somewhere in the RDF document, then C is a class. Yeah, so if I have this triple, then this triple should be derivable. C is of type class. And similarly, all other examples. Say here, if C is of type class, then C is a subclass of resource. Every class is a subclass of RDF resource. Or here, if I just write C1 RDFS subclass of C2, then naturally C1 is a class and C2 is a class. Yeah, and all this kind of natural things which are nearly obvious to us or obvious to people with some primitive mathematical education, but not for a computer, because computers never had any primitive mathematical education. Now, so if we apply all these rules, we'll obtain something like this. Yeah, you see, it's becoming a little bit unreadable. Any errors missing here? Right, to understand what is missing, let's consider now the semantics of subclass and class. The semantics is, as I said at the beginning, very similar, if not identical, to set theoretic semantics. Yeah, subclass means RDF subclass means this subset relation in mathematics. Yeah, with all consequences. If X is a subclass of Y and Y is a subclass of Z, then X is a subclass of Z. Okay, and type means this element, yeah, membership in a class. Yeah, say MZ is an instance, an element of some class, some classes, professor, academic staff, and so on. Yeah, or resource. Okay, if we take all this, sorry. Oh, right. So about properties, sub-properties, we have the rules like this. If, similarly, if P is a sub-property of P, P1 is a sub-property of P2, then both P1 and P2 are properties. Now, sub-property is a reflexive relation on properties, which is natural. Any property is a sub-property of itself. And also, sub-property is a transitive relation, yeah, like a subclass. Okay, so if I add all deductions using this rule from the diagram, from the original diagram, okay, I jump immediately to this one. You see that everything here is transitive. Sorry, yes, transitive, and everything is reflexive. Yeah, reflexive means this arrows. Yeah, that a class is a subclass of itself. Yeah, and transitivity means this, that MZ is of type professor. Professor is a subclass of academic staff, so MZ is of type academic staff. So there are some rules for domains and ranges. Yeah, for example, if we have a triple like this, P RDFS domain C, then P must be a property and C must be a class. Yeah, and also we always have the following axiomatic triples. Oh, they must always hold in any RDF document. Okay, so as far as I know, this should be the full picture. Yeah, where everything implicit is explicitly represented. Maybe I missed something. So we started with the 7 ellipses, now many more, and the model shouldn't be the arrow from module to stored by. Okay, let's see. Module is stored by. Okay, I don't know. So the module say semantic technologies or semantic web is stored by MZ. If I want to say the other way around, I would say that MZ teaches yeah, so a lecturer teaches a module is taught by MZ. And so as far as I understand, it is correct here. So there are, and we'll come to this a little bit later, well, you should distinguish between inverse properties. I mean, module is the domain of is stored by, that's true. Module is the domain is stored by domain module. This is what's written here. That's true. And academic stuff is okay. Yeah, as is stored by, this is the property. And the domain is module. So the arrow is okay. Let's see. Let's see, where did I write it? Domains and ranges. Okay, this is what I write, that say author of range something. So the triple is author of, then arrow to the range. Oops. So I start with module, then domain arrow goes, sorry, no, I start with is stored by, this is the property, then domain, that's an arrow, and goes to module. So the arrows are correct. Okay, so this is what I wanted to say you about RDF and RDFS. Now, in a 3 minutes, I'll introduce a much simpler syntax, the turtle syntax. But before that, let me remind you of a very dangerous danger, super dangerous danger, when you deal with things like a class of all classes. Probably you know, or I don't know whether in your department how far they teach logic, mathematical logic, and paradoxes. But the story here is like this, that sets, classes, and so on were extremely popular in the second half of the 19th century, yeah, when set theory was developed, in particular by a guy called Georg Cantor. It's a German mathematician who developed set theory, and he and his colleagues show that in set theory you can define many, basically the whole mathematics. Yeah, so you can start with the empty set and then construct, say, the set which has a single element, and the single element is the empty set. Yeah, and then a set with two elements like this. Yeah, so, and this will be 0, this will be 1, this will be 2, and so on. So by doing this, you construct all natural numbers. Then by taking subsets of natural numbers, you create real numbers, and so on. Yeah, so that was still is a very nice theory, set theory with nice things, cardinals, ordinals, and so on. And mathematicians and logicians were very happy. They started writing books about this. And then in 1901, yeah, this guy on the picture sent a letter. He unfortunately didn't have, they didn't have emails in those years, so it was a physical letter. And this guy, Bertrand Russell, sent a letter to, I forgot what's his name, another logician, where he said that, oi, 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 we are in danger, and described the following paradoxical construction. Yeah, so he said, Russell said, consider the following set, this one. Yeah, and in set theory, everything is a set. Yeah, whatever you have, everything is a set. Say 0 is the empty set, 1 is this set, and so on. And so all things are sets. And then how you can construct new sets, you say that, okay, I take all the sets that satisfy a certain property, you know, like this. So P is a property. All right, and then Russell said, let's take all sets B such that B is not an element of itself. Okay, let me clarify. Say 1, is 1 an element of itself? No. The set of all natural numbers, is it a natural number? No. Yeah, so all these examples are then in this set A here. But then I say, okay, how about B, the class or the set of all sets? How about that? B, it's a set, so and it's the set of all sets, so it must be an element of itself. So B is not an element of this set A. Right. Okay, so we take this set A of all sets that are not elements of themselves and ask this following question. Is A an element of itself? Right? So there are two possible answers. It's indeed the case, A is an element of itself, but then you look at the definition of A and see that it cannot be the case. So that A is not an element of itself, but then by the definition of A, it must be an element of itself. Okay, it's madhouse. Yeah, it's a contradiction. This paradox, this construction since then is known as Russell's paradox. And it started some new developments in logic, set theory, mathematics, and so on. So there is a popular version of this of Russell's paradox, yeah, in the form, say, of the barber paradox, which is well known. Yeah, so imagine that there is a town, a village, and there is only one barber who is a male, and according to law, in that village, they also have a parliament, and the parliament is very sophisticated, and they adopted the following law. The barber shaves all and those old men in the town who do not shave themselves. Yeah, so the question is, who shaves the barber? And in the same way as with the Russell paradox, there was no answer to this question. And the conclusion to this barber paradox is very simple. Such a town, such a parliament, such a law cannot exist. Yeah, it's easier, just nothing like this. But Russell's paradox is in mathematics. Yeah, so you can't just delete all the mathematics. Anyway, so why I started saying this? Because in RDF, we have the class of all classes, say here, the class of all classes, and so on. Fortunately, in RDF, we don't have paradoxes like this for one simple reason. RDF does not have negation. Yeah, and negation, not, is very important here in Russell's paradox, yeah, because here it's B is not an element of itself. Anyway, if you ask me personally, I don't like the situation in RDF where somebody introduced this class of all resources, class of all classes. That doesn't look nice, and I think mostly people never use it. Okay. Turtle, TERS, RDF, triple language. Yeah, so this is another RDF syntax. There are many of them. And here you can write, using this syntax, you can write your documents in a natural way. And this is what I'm going to ask you to do. So here I give an example of a complete Turtle document. Let's try to figure out what's written here. This is clear, it's a comment. Then this line, the prefix, it describes, introduces namespaces. Yeah, remember that in RDF, namespaces are very important. And what's the meaning of this? The meaning is this: if anywhere in the document I have DCS colon, like here, yeah, then this DCS 2 dots will be replaced by this bit, yeah, which will produce a proper URI. We declare these things in the beginning, and then just use namespaces like DCS. Now, when you write your own RDF documents to answer my questions in the test or whatever, then you produce some namespaces or namespaces. For example, if you have your own local namespace, just write something like example or something, or even this would be just a column, which would be better than no namespace, no prefix at all. Okay, so I have one to you. Now let's read the remainder. The remainder is just a set of triples. A triple, subject, predicate, object. So you see that the object is a literal, a string of characters, and that's why it is in quotation marks. The end is full stop. This is the end of a triple. And all of these things are like this. So this is a full unabridged RDF document written in Turtle. Of course, there are lots of abbreviations. I'm not going to show you all of them. If needed, you just click here and or Wikipedia, and you will find basically all the agreements in the turtle language. Just mention the following, that if I want to be lazy, say here 3 times I have the same subject. Yeah, instead I can write something like this. Yeah, I write a triple, full triple with this subject, and then semicolon. Yeah, no, not full, but semi, and then I omit the subject and write only the property and an object. There are some other abbreviations, as I said. I don't know all of them myself. Now, another thing is, instead of RDF type, you can simply write A. Yeah, like you read MZ is a person. Now, namespaces. You see that here is my own namespace, which I introduce here. There is the RDF namespace. It should be also specified if you use this. What else? And here there is for of. Yeah, it's a, and here, yeah, there is a vocabulary called for of, friend of a friend. Yeah, so it presents a vocabulary about people. Yeah, and this is the logo of for of. Okay, so let's have a look at blank nodes in this turtle language, because they are quite interesting. So let's consider this document. Here I give the namespace for of, friend of a friend. Yeah, this is the URI. And the document I have here says that there exist 2 people who know each other. But note that I write here underscore colon Alice. This is supposed to be, or supposed to denote, a blank node. That is, this is not a URI. Yeah, it's not a URI. It's a blank node. So everything that starts with the underscore is a blank node. Yeah, so there is no URI. You can't find any URI here. Similarly with Bob, underscore Bob. So underscore Alice knows underscore Bob doesn't mean that there is a URI of Alice. Yeah, it's just, you can rewrite it like this. Maybe it would be better. P1 for of knows underscore P2, full stop. Yeah, or X and Y. So the meaning of these 2 sentences is indeed like this, that there is somebody who knows somebody else, and that somebody else knows the first someone. Or they exist 2 people who know each other. Okay. Another way of representing blank nodes is using square brackets like this. Yeah, so let's consider this document. It says that someone knows someone else with the name Bob. Right, so if I use the underscores, I would write like P1 for of knows somebody else, P2, full stop, and this P2 for of name Bob. So these two documents are equivalent, but you see that using square brackets, it's shorter. Yeah, why I need square bracket here? Because P2 occurs twice. And this underscore P2 refers to the same someone else. That's why we have the square brackets over there. Okay, now, of course, the syntax can be pretty unreadable. Say this document, square brackets contain for of name Alice. That is, somebody has name Alice, and this somebody knows somebody else whose name is Bob, who knows somebody with name Eve, and so on. Yeah, so I try to represent it with the explicit blank note here. So somebody has name Alice and knows somebody whose name is Bob, who knows somebody third whose name is Eve, and Bob's this email address is Bob example, so on. Okay, so it can be pretty sophisticated. Now, what are the uses? What is a good practice of using blank notes? Here, I have a few examples in this document. Let's have a look. So here we have a URI. It's a resource, and it's the subject of the following triples. The title is Web Data Management. Probably it's a module. And there is a professor, probably who teaches this module. And here you see we have a blank node. And then we have students with a blank node. And then we have some provenance information also with a blank node. Why? Let's consider professor. So this is the blank node underscore B. And what does it do? It just collects some complex information, complex attribute. Yeah, what information is given about the professor? His name is something. He has a home page and he has an address. These three triples: full name, Adam Smith, home page, address. What is address? Again, it's a blank node. Yeah, because in the address, in this next block, there are a few items like the street, also type, address type, street, number, postcode, city. Now, for the students, it's not a single student, it's a student, a number of students. So we use a special data structure, bag, once I mentioned it, yeah, and it can collect a few individuals. Say here we have S1 and S2, yeah, and so on. And here, A1, this is a provenance information that records when this document was created, who updated it, and so on. Yeah, a very important thing in modern data representation. Yeah, we don't want to have fake news. So we should be able to see the provenance information. So these are typical uses of blank nodes in practice. There are other uses as well, but this is mostly you'll need this ones. All right, so a quick introduction to the Turtle syntax is here. Turtle is a W3C recommendation for about 5 years now, and so on. Yeah, and there are various pieces of software that translate Turtle into the XML syntax and so on. Okay, so let me finish before we consider some examples. Let me finish by a few general observations. So where is RDF on the web? First of all, in some small RDF graphs, which can be represented in XML or Turtle, and so on. Yeah, there are some data sets or vocabularies like FOAF. These are all RDF files. More importantly, RDF data are available from the so-called SPARQL endpoints. SPARQL is the query language for RDF. Endpoint is a very ugly looking window where you can, or your computer agents can query data, the RDF data. For example, many governments in Europe provide a lot of information about many things in the RDF format. Libraries provide information about their books in RDF format, and so on. There is a version of Wikipedia in the RDF format. For example, if you go there, you will have, or your computer agent will have access to Wikipedia, this databasepedia, yeah, and you can query this in SPARQL, yeah, or here is probably RDF, no, I don't want, RDF triples about Norway, and so on. So this is the main use of RDF on the web. Yeah, different countries, different organizations provide RDF sets because it's very easy, because you don't have to know the schema like in databases. Yeah, here everything is a triple. And we'll see some examples how to query RDF triple stores, how to use these RDF endpoints and query triple stores. All right, and by the way, there are many programs available for free or for payment that convert, say, relational data in RDF or CSV, Excel in RDF, and so on. Okay, that was one observation. Another one, how to create RDF data and vocabularies if you want to do it and to, publish it on the web. Shouldn't be a big deal. The only real problem is that designing an easy to use and robust namespace is non-trivial. Yeah, you have to invent good names and good terminologies, good vocabularies. So instead of inventing something, yeah, maybe it makes sense to have a look somewhere, say here, for existing vocabularies. Yeah, because say if your job, if your company asks you, okay, design a, I don't know, an ontology and RDF representation of, say you work for a music company, so some information about records they have, about singers, and so on. Yeah, maybe it doesn't make sense to design everything from scratch. Maybe it makes sense to have a look at, say, this list of linked open vocabularies, LOVE. And here you will find 654 vocabularies of various type. Geo, time, event, lots of stuff. I don't know what Aragon interoperable information structure ontology and so on. Okay, just wanted to say that a lot of things have been already developed. What else? There are some best practice documents about, or recipes how to publish your data on the web. Yeah, or look at the linked data tutorial. I said that most probably all the terms you need have already been defined somewhere. Now, what kind of vocabularies do we have? To begin with, there is the RDF vocabulary. In RDF, what we have learned, we know that we have type. Yeah, links a resource to a type, to its class. A resource, yeah, the type of all resources. Property, the type of all properties. Yeah, so in some cases, we can write triples like this. Say we are after some geographic information, and we write Berlin is of type resource. Yeah? Geo contained in a property. Contained in is a property. Type is also a property. Yeah? So everywhere here we use this RDF colon things. So this is the proper RDF vocabulary. We have already seen a friend of a friend. Yeah, this is the URI of the FOAF project, and there it's basically about people, about persons. Like, person is a class of all people, alive, dead, real, imaginary. So Sherlock Holmes is there as well, probably. Name is a name. You can distinguish between first name and family name. So these are also classes. Mbox, it's a mailbox, and nose, well, clear what it means. Yeah, for example, we can write things like this. Yeah, say that my URI is of type person, name, mbox, and knows, or I know myself, for example. Okay, another very big vocabulary is called Dublin Core. And for many years, they have been developing metadata, how to write metadata for documents. A huge effort. So what do they have? Things like creator. Yeah, you have a document, and the main author of the document, creator, created the creation date. Description replaces when one document replaces an older version. Yeah, say here what this URI, that's me, is the creator of something about myself, the date of creation. Here, some description, and replaces my old homepage. Okay, and my last example is this one. It's DBLP. It's a computer science bibliography. It contains nearly all the, not all, but nearly all publications in the world. It contains, say, if you go there, computer science publications here, and well, I don't know, let me say, if I start writing myself, yeah, oh. Yeah, so oops. Yeah, there are my publications in human readable form, but you can also find the same information in RDF form. It should be somewhere in this gray line in the middle. Yeah? So your computer agents can query this information. And there you have things like the author of a document, title, name, affiliation, and so on. Okay, this is what I wanted to tell you about RDF in RDF schema. Next time we'll be considering the query language for RDF. In your test, you will have a few questions on representing some information in RDF and understanding RDF documents. So I have some examples, and I think they are on the web as well. Just a second. So there are some exercises. So what I suggest is that let's have a look and discuss these exercises. And I'll provide you with model answers. So what I suggest is that you try and answer these questions yourself. And next time I'll provide answers on the module webpage. So questions will be like this. This exercise 1. Describe in English the information from the following RDF document, which is given in the turtle syntax. All right, let's have a look. What is here? Namespaces in base. Okay, so some speaking names. You see royal family, so probably it's about some royalties. Royal UK, so probably about the royal family in the UK. So the question is, describe in English the information from the following RDF document. Well, probably namespaces aren't that important, so let's omit them. Let's read the first triple. A URI, something about Elizabeth II. And the first triple, it says that this URI is of type woman. And you see that this is what I didn't tell you. It's comma. And comma here says or means that the subject and property are the same as in the previous triple. So this means that, so the first one says that Elizabeth II is a woman who is a British monarch. Okay, now we have semicolon. This means that the subject stays the same, but the predicate, the property, and the object will be different. And then so we have here one triple, another triple, first, second. Then we have Elizabeth II has child, Charles, Prince of Wales. Third triple, she has child Anne. Fourth, Prince Andrew. Fifth, Prince Edward VI. All right, and she is child of George VI and Queen, so it's 7, 8, and Queen Elizabeth, the Queen Mother. And finally, Elizabeth II is married to Prince Philip. So in total, the main body of the document, of the RDF document, contains how many triples? 9 triples. So if you have something like this, then you are asked to, return 9 and to write in probably English, in plain English, readable English, the content of this document, which should be something like this, that Elizabeth II is a woman who is also a British monarch. She has children, Charles and Andrew and Edward. Her parents are George and Queen Elizabeth, and she is married to Prince Philip. Something like this. Okay, so this is one type of questions. It's the easiest one. A harder one is here. Represent, if possible, because not all information can be represented in RDF. For example, negative information cannot be represented. Yeah, something is not a, I don't know, Homo sapiens. Yeah, not cannot be represented. Okay, represent as if possible the following information in RDF using the turtle syntax. Yeah, and here I have 2 sentences. The journal article, and this is the title, was written by Nigel Shadbolt, Wendy Hall, and Tim Berners-Lee, and published in IEEE Intelligent Systems. That's the first sentence. The second, Tim Berners-Lee was born on that date in London, England. Yeah, and here are some versions. Using your own vocabulary and URIs. Yeah, that's one scenario. Another scenario, for integration in Yago. Yago is some vocabulary and data set, and you just Google Yago and use the vocabulary provided by Yago. Now, I'm not going to do this. Or for integration in DBLP. Yeah, and I showed you a DBLP web page. Okay, so let's try to answer question A quickly. So at the so I don't care how to what kind of classes to use. The problem, my problem, is to somehow represent the information. So what is the situation? Yeah, probably I should draw a picture to begin with. The journal article, The Semantic Web Revisited, was written by. How to draw a picture for this? How to represent the journal article? Yeah, definitely it's a subject. Yeah, so we need this subject. Yeah, this journal article. I don't know, article. Yeah, this is my pictorial representation. And then what? Journal article. What is this? This is the title of the article, right? So maybe I introduce a property, say has title, and then the Semantic Web Revisited. This can be either a literal, the Semantic Web Revisited, or alternatively, maybe there is a URI for this paper. Yeah, there is some web page where this paper is. Maybe there are some further data about this paper. How many citations, for example? Yeah, so it's a a decision whether provide the URI or literal. Yeah, literal or URI. It's your decision. Right. Then was written by, so authors. Oh, I forgot one thing. Sorry. It's written journal article. Right, so this art is of type. Yeah, so here I use RDF type. Yeah, and it will be journal article. That will be a class. Yeah, say these can be taken from DBLP. Right, as is of type, title, and then was written by. Yeah, and then is written by, and then how shall we proceed? It can be, maybe it can be like this, is written by, and here I have, I don't know, URI for Nigel Shadbolt, say NS, and here name. And then it will be a literal, Nigel. And then another one is written by. And the next one will be what? Wendy Hall, WH, and then name. Or differently, or you can include the name, this name, already into a speaking URI. Like in the previous example, you see we had here Elizabeth II. Yeah, it was already a speaking URI which gave her name. And then our journal article, and another one, I don't know, published by, for example, published by. And here we give a URI of IEEE Intelligent Systems. We can find it on the web. Every journal has it. Okay, so this is your pictorial modeling. Yeah, and then you'll have to represent this information using proper namespaces as a turtle document. As you see, there are many considerations here, or say authors. We have 3 authors here. Yeah, maybe you should create an anonymous resource that is linked then to all the 3 authors. So there are many decisions to be taken, and different vocabularies and so on. So next time I'll publish my answers to these questions for your reference. But these are the, maybe next time we should have a look at exercise 3. Because here there are some examples with statements about statements, yeah, like number 6. John believes that Mary wants to marry him. Or John believes that Mary is at home. And some temporal information here. Okay, so we'll start by considering this next time. And then next time we'll move on to the query language, Sparkle. Any questions? No, I don't hear anything. Then that's it for today. So see you next week. Bye.